Welcome back. First of all, I want to thank everyone who watched the first video, and I want to give an especially uncomfortable parasocial thank you to all of my 12 subscribers. You guys complete me. Hopefully this video sounds better than the last one. This is the second time I've recorded it. The first time I recorded it in my school's quote-unquote podcast recording booth, which ended up being a terrible idea because the mics were just... Anyway, if you remember from the last video, we made an app which runs on an iPhone that creates images using Apple's TrueDepth system. Maybe you should watch it or something. Never mind. Remember, the footage created by that app was very choppy. That's because it was running at a terrible frame rate. Let's quickly assess what that frame rate was. So I've added a quick and dirty functionality which prints the frame time in frames per second in the debug terminal. Put down your pitchforks, people. It's just temporary for this demonstration. If we run the app, we can see that it's hovering at a
13 FPS, baby.
That's the kind of frame rate you would expect from a PowerPoint presentation or AI Minecraft or something. But it's not good enough for me. So let's get into our optimizations. I've used the word parallel processing in the title, but what does that mean? Well, in order to explain what parallel processing is, let's talk about the parts of a computer. Most of you know that all computers have a CPU or processor. Some computers, especially of the gaming variety, have a GPU. What's that? Well, a CPU is good for complex tasks, and a GPU is good at doing simple tasks 1,000 times at once. Let's look at a hypothetical game for an example. Let's say that our game needs to handle the world, physics, enemies, and the graphics. If we gave all of these tasks to the CPU, it would have to do all of them one at a time. This is called serial processing. But let's say in this scenario we have a GPU. What tasks should we allocate for it? What sort of tasks would the GPU be good at? To answer this, let's understand the limitations of the GPU. If this guy is the CPU, then this is the GPU. One of these guys is called a thread. A GPU has a given amount of threads which can be dispatched to complete tasks. Each thread is like a much dumber CPU. There's one more important detail to how a GPU works. These guys cannot talk. A GPU thread cannot communicate with other threads. Each thread needs to do their tasks independently. They can meet up at the beginning and end, but they cannot collaborate. This limitation is intrinsic to parallel processing. Now, knowing what our GPU's skill set is, we can go back to our list of tasks and decide which one is suitable for the graphics processing unit, GPU. That's right, a GPU is specifically designed for graphics. Parallel processing is the perfect task for this because each pixel's color can be calculated independently of the others. So, the pixels are divided into groups, and each group is passed to a thread. Then, the threads work away to calculate the color of each pixel, and then they meet back up. Reconstruct the image and bam, you have graphics. When a computer doesn't have a GPU, the CPU can take the work up, but it's going to be slow since it has to do the work of all of the threads one at a time. That's what this means. Now our app doesn't have graphics per se, but it is generating an image. As a matter of fact, the image generation is the worst performing function of our app, and it's the main bottleneck for performance. This is because all of our pixel colors are being calculated serially, when we could be saving a lot of time by processing them all at once. Our current method is equivalent to integrated graphics, which is why, unsurprisingly, it runs like So let's switch our rendering from a serial processing model to a parallel processing model. How does one do that? Well, normally it involves splitting your program in two. One side will run on the CPU and the other on the GPU, in a graphics-specific language such as Vulkan or OpenGL. Does this mean that I'm finally free from the hell of writing this thing in Swift? Well, unfortunately, no. Our app runs on an iPhone, and if you haven't realized, this thing does not have a graphics card. But here it is playing games, so how? Well, allow me to go on a barely related tangent. The world is changing, and if you ask me, the times of having a CPU and a dedicated graphics card are swiftly fading into memory. Several modern devices don't have a GPU at all. This includes the iPhone and your Apple products. Now I know what you're thinking, those aren't very gaming. Well, what about the Steam Deck and the PS5? It doesn't get more gaming than that. Both systems have been praised for their performance. I can hear you asking, how is that possible? Well, it's because of this, the APU. It's the midsection of the Venn diagram of computer parts. It's the passionate love baby of the CPU and the GPU. It stands for Accelerated Processing Unit, so enjoy having that useless piece of information until you die. APUs are growing in popularity. They are capable of behaving like a CPU and a GPU at the same time, which is why their application in gaming is so appropriate. If you ask me, and keep in mind I am the first person to ever say this, APUs are the future. But we're off topic, let's get back to the iPhone. The iPhone has one chip. It's called the Bionic chip. What does that mean? More often than not, things have fancy names because they were invented by nerds who like fancy sci-fi names. Well, Apple doesn't call the Bionic chip an APU, but if we say that an APU is a chip which can function as both a GPU and a CPU, then the Bionic chip definitely qualifies. So what does that mean for our app? Well, it means that the entire app is going to run on one chip, which means one language, which means Swift. Swift is capable of having serial processing and parallel processing, which makes sense since it is applied on a chip which can behave as a GPU and CPU. Now, I don't like Swift. I do not like Swift. Now, Swift is a language which I do not like. Some would even say that I do not like Swift. I know what you're thinking. I do not like Swift. And let me assure you, I do not like Swift. This is because I do not like Swift. Swift is not that bad. There are even some things about it I like. At the very least, it's a curly bracket language. Reminds me of Mom's home cooking. It's just so proprietary and convoluted. There's a special number system that exists just for iPhones. Really, guys? Regular numbers aren't good enough for you? Another thing that I found interesting is that Apple's internal system uses meters instead of freedom units, despite being an American company. Unpatriotic communist bastards. So a very painful refactor later, I did it. I divided the image into 4 groups and allocated them to 4 threads. Then we merged the results into one image. Here it is working. I have never made a mistake in my entire life. Okay, this seems to be working more as we expect. And just looking at this, it already looks smoother. Let's take a look at our frame rate. Okay, this is great. It's functioning at a smooth 30 frames per second. Let's try brumping. Let's try bumping that frame cap up to 60. 60 seems to be no problem. Let's try the smoothed buffer we discussed in the previous video. It can handle that as well. Well, that's great. Parallel processing seems to have been the solution to our performance issue. I've tried pushing the frame rate past 60, but the IR sensor picks up data at 60 frames per second, so that is our limit. Let's take a look at our app's performance in the debugger. This is before. You can see that it is hitting near 100% usage, and this is after. Why is it like that? There's no over 100%. Also, the previous version made my phone noticeably hotter, and this version runs cool as a cucumber. Well, the truth is, this CPU usage thingy here is pretty misleading. The maximum value that could show up here is 400%. It's displaying the sum of the performance of all cores. So before, we were using one core at 100% capacity, and the other cores were just waiting around. Now, we're working with several cores. No one core is working as hard as before, which is why it runs cooler. The cores can easily tackle their portion of the image, even if the sum of their usages is greater than before. That's why it appears higher, but is actually running more efficiently. Let me address something from the previous video. I talked about a lot of different palette generation methods. All of them are implemented in the Python repo, but only 3 got ported to Swift. The singular linear interpolation, multiple linear interpolation, and the cosine waves method. In the previous version, the multiple alert method worked, but it was definitely the worst performer out of the 3. It was struggling to hit 12 frames per second. That's because it's the most complicated algorithm for generating a color. Now that we've split the task and given it to the dumber parallel cores, it's causing some strange effects. Let me explain. One of the words that keeps popping up when learning about parallel processing is asynchronous. It means that you can't assume all of these cores are doing things at the same time. They're trying to keep up with the frame rate, but for any given frame, they each take a different amount of time to complete their portion of the image. In this way, the cores are detached from each other and the entire system's understanding of time until they complete their portion of the image. That's why when they have more work than they can complete in a frame, the video output itself gets slower. This leads to a time slow effect. Here's a good example. Assume that this person is walking at a continuous rate. As you can see, when I switch to the poly palette, time slows. Now it gets more and more out of sync with real time the longer it runs. I'm sure that eventually this will fill up my memory and cause my phone to crash. So I'll just turn that off. I really tried to fix this, but I couldn't find anything that would optimize our palette function. That's where you come in. I've posted this exact script. Have a look and comment your solution for optimization. Whoever has the best idea, according to our panel of non-biased judges, will receive a genuine thank you from yours truly. I mean, this is a rare, limited edition item. You guys want this. While I wait for one of you to solve my problems, I'll do the responsible thing and remove the feature from my app. Rest in peace, Poly Palette. While I'm, quote, improving things, there's something I've been wanting to fix for a while now. Right now, the numbers behind the palettes are hard-coded in. I can change them in the code, but come on. It's high time that I applied some of my world-renowned UI design to this problem. Apple makes it so easy to make beautiful UI with their Swift UI system, and I just refuse to make anything that doesn't look like vomit. The good news is, now you can customize the values used by the palette functions. you can make it lerp between any two RGB colors and change the scales of the individual cosine waves used in the cosine palette. Since it's a cosine wave, they all start at 1, which is scaled and translated to 225, aka it starts at white. And whenever the palette repeats itself, it goes back to white. By making these scales values with a common factor, you can make it repeat to white at different frequencies. I'm sure I've done a terrible job explaining this, but you really got to experience it yourself and run your own experiments. You can look forward to that when the app is published. More information about the future of this app at the end of the video. While I'm making travesties to the good name of Swift UI, I might as well improve the animations, which have up to this point been me sliding my finger along these sliders. Using this panel, we can input an animation step and have it animate smoothly and beautifully. Now that we've vastly improved our app, I think it's time for another music montage. Well, that'll have to be all for now. If you like this video, make sure to express yourself by liking and subscribing and commenting and all of that. I'm super interested in publishing this app, but in order to invest the time and money that I would need to put this on the App Store, I'd need to get a lot of internet validation from you guys. Make sure to spam email everyone in your contacts with this video and watch it 50,000 times. And if you made it this far and you haven't watched the previous video, check it out. It'll make what you just watched make a lot more sense. In the meantime, thank you for watching, and I'll be around. Peace.